Hi everybody, my name's Charlie Newbold. I've been project manager for Hydrostar for this discovery phase, and I'll be taking you through our project, NextGen Electrolysis Wastewater to Green Hydrogen. Next slide, please. So the challenge we've been focusing on is obviously challenge 3 to improve energy system resilience and robustness. Now, Wales and West and other gas networks nationally are investing heavily in preparing the network for large quantities of green hydrogen being injected and understanding the effects hydrogen will have on the network. But at present, green hydrogen production is limited by operational constraints and infrastructure requirements. I'll come on to these more later, but two of the key considerations are where do we get the electricity from and how do we obviously supply enough water for large-scale hydrogen production. Now, the reliance on the electrical grid and mains water infrastructure is limiting the locations that green hydrogen can be produced, and therefore the resilience of gas network supply and the ability to control where hydrogen is flowing within the grid network. This is also affecting the costs of production through requirements for compression and transportation. So next slide, please. Our project really is seeking to address these issues and others, with our objective being to lower the operational barriers of green hydrogen production by using water that is less pure, addressing real-world manufacturing and operational constraints, and reducing hydrogen production cost. We've placed particular emphasis on the water component of green hydrogen production. Now, current electrolyzers are using pure and ultra-pure water as feedstock, and this has a very high water demand, not just from the direct production of hydrogen, but also during the purification process. So to make 1 litre of purified water, there's actually at least 6 litres of water which is required. And this is posing threats to water supplies in specific areas across the country when hydrogen is scaled in line with government targets, particularly in areas where water shortages are a common occurrence over summer. So therefore, this project has investigated different levels of water purity, starting with tap water. This obviously isn't a waste source, but it's not an ultra pure source like the highly purified water. And then also using water like rain and storm overflow water from rivers. But just being able to use the wastewater isn't the only consideration from a lack of infrastructure perspective. So it's also to do with electricity availability. So we've been modeling matching electrolyzers to fluctuating renewable production, which combined with the water side of things facilitates a more distributed approach to hydrogen production. And the benefits of a more distributed approach is really what is increasing the resiliency, how this project is looking to increase the resiliency of network operations. So being able to inject hydrogen into specific nodes along the network, it allows us to control hydrogen movement into specific lines, which are strategically beneficial for network operators, but crucially also reducing the cost for network users by removing compression and transportation. Next slide, please. So moving on to kind of some of the work undertaken, I'll start with what the water usage and the electrolyzer. So we looked in detail at rainwater in Exeter as the initial wastewater source, and the analysis of the rainwater really found that we see consistent ions in the rainwater, but that the concentrations of these vary. So you can see month to month there that obviously the concentrations of each of the different ions are going up and down. Now, this to kind of account for this, we developed the chemical equations to predict the potential byproducts from these different ions, and therefore, what the considerations for what we'd have to deal with by utilizing water that isn't super pure. So these really have guided the considerations for Alpha in terms of electrolyte composition and electrolyzer specs. So from an electrolyte perspective, the electrolyte is going to need to be changed slightly dependent on the concentration of ions present in each batch of water. So, what we'll start to look at is, how much do we need to change specific components within the electrolyzer to match to basically the batch of wastewater that's being used. And then from an electrolyzer perspective, what are the different materials that we can use for the electrodes to account for the different byproducts, and also the power levels that we can use within the electrolyzer to see how that will affect the different byproducts that are produced. Next slide, please. So we also wanted to look at the different components of the green hydrogen supply chain. Now, we mapped and modeled production, all the way from kind of generation of electricity, compression, water usage, etc., all the way through to use and consumption of the hydrogen. So doing this highlighted some key areas that are facing large demands that can be minimized to increase overall efficiency rather than just a single point efficiency, and therefore reducing the cost as much as possible. And two of these were obviously the compression and the transportation element, which using a distributed production strategy helps to reduce. Can we click on one, please? Thank you. So we also looked at the matching to fluctuating renewables and using a techno-economic model to predict the hydrogen outputs from the different sources, and also the cost that this would entail. So obviously the first one at the top there is the solar graph, and the second one below is the wind profile of matching to hydrogen production. So what's interesting about the solar one is when the water is most plentiful, i.e. in the summer, when the water is the least plentiful in summer, but the power is the highest available, that's what's going to make an issue for the water consumption if we're using highly purified. Whereas for the wind profile, it actually fits quite nicely as to when we're going to expect there to be more wastewater being produced. And what this also showed was to flatten out the kind of the capacity factor of the electrolyzer, actually using a hybrid system of the two would be very beneficial. Next click, please. We then also took an initial analysis into gas network operations, primarily methods and locations for injection. So we looked at some high demand users that Hydrostar have been in contact, kind of working with for quite a while, and then mapped the network routes around these sites to identify potential injection points which would be beneficial to a network operator, but also deliver the required quantities of hydrogen to the off-taker. And identifying the key injection points also has a large resilience benefit, but I'll cover those further down. Next slide, please. So in terms of the potential benefits, now this is essentially looking at using just tap water without the need for purification. So not even looking at waste sources straight off the back. Now, we can save an estimated 4.5 Olympic swimming pools per gigawatt of electrolysis per day by just simply removing the need for highly purified water. So not even using a wastewater source yet, just removing the need for purification. And when you factor in the usage of wastewater still, it reduces it by basically another Olympic swimming pool daily of mains water. Next tab, please. And to put this in a scale which is actually kind of relatable to, that's 7.65 million kettles filled daily to achieve the same amount of water consumption. So it's an enormous amount. Next click, please. And also just another one, if you were to take a 10-minute shower each day, you could have 385 years worth of showers for just for 1 day's worth of purified water demand. Next slide, please. Thank you. Then also looking at the other side of it, which is the not the water element, but the other elements of compression, for example. If we just remove the need for compression up to 300 bar across the course of a year, it's the same carbon saving as taking 17,600 cars off the road. So, a massive saving really in carbon. Next click, please. And that's also equivalent to over 400,000 standard UK homes equivalent electrical demand for the year. And then we also quantified this in terms of the cost of, removing compression, removing the need for purification and the transportation of hydrogen. And we were seeing, between a 20 and 24% reduction in the cost of hydrogen across its lifespan. Next slide, please. So how's wastewater usage and mapping and modelling the different demands across the hydrogen supply chain relating to user needs? First and foremost, these strategies are, to reduce the cost of hydrogen, both from an initial capital expenditure and operational energy perspective. And this is obviously currently a key barrier to wide-scale hydrogen usage. Next click, please. We then have greater modulation of hydrogen flows across the network. Now, by generating hydrogen in a distributed manner without needing significant water or electrical infrastructure and injecting into specific nodes, tracking hydrogen movement is far easier for a network operator instead of it just going in one location and then being consumed somewhere downstream. And it also enables network quantities and pressures to be kind of reinforced, but more significantly, it reduces a single point of failure. So in the event that one hydrogen generation plant comes offline for a period of time, the other generators along the network are still operating and delivering hydrogen, instead of extremely large plants, which if they go offline have significant effects on network levels of hydrogen. Next click, please. And then the case of sensitive users with different needs. Now, some users will need high concentrations of hydrogen earlier than others, and by injecting into nodes along the network, we can deliver this without forcing current users who are constrained to higher purities of natural gas for a period of time because they've just bought new plant. So this basically, if it would cost them too much to immediately switch to, not immediately, but within the next 5 to 10 years, switch to hydrogen usage, we can still actually modulate the amount of hydrogen natural gas that they're going to receive. Next slide, please. So with this in mind, we are seeing a lot of opportunities being created from using less pure water and injecting in a distributed manner. So one of the things that we're going to start looking at in the alpha phase is actually using processed wastewater. So not just from rain or from kind of storm overflow, but actually, water from processes used on site. And, there's the potential for a bit of a co-location strategy there in terms of using their on-site wastewater and then turning it into energy for usage on site. We can also look at, reduce reliance on water supply, which enables a more guaranteed production. So particularly in areas which are facing water shortages, like I mentioned earlier, actually, if we can use the wastewater sources available, we're not constrained just to the mains water that's available. Now, distributed production at certain nodes of the gas network, this is essentially to increase the resilience of the network. So how I talked about the reduction of a single point of failure and actually having lots of different generators to inject into different branches of the network and supplying the hydrogen exactly where it's needed at this point in time. And then also that results in lower costs from removing the need for any sort of transportation of hydrogen or compression to get it into the network, because we looked at different network line pressures, and actually the electrolyzer will output pressure that's higher than network levels anyway in the lower pressure lines. Next slide, please. So our thought evolution throughout discovery, it's really been guided by the feasibility studies confirming that using wastewater and other strategies can be very beneficial to hydrogen costs and resilience of production. Now, the key development really is focusing on co-location and a multi-focus strategy. So from customer perspectives, potentially utilizing processed wastewater to create their on-site energy requirements, and also, you know, in certain cases, looking if we can utilize the oxygen on site as well. And then for networks, being able to inject at specific nodes to, you know, to track more easily where the hydrogen is in the network. So therefore, with alpha focuses for next steps, what we're really going to look to do is start developing some actual kind of physical experiments. So first of all, well, I'll start with the electrolyzer. Actually, we're going to look to create a kind of 2 kilowatt unit, which we can start to do some tests on wastewater at a small scale, just to see, you know, how it will react to utilizing different wastewaters. And then to match with that, we'll be modeling the electrolyte usage across the changing concentrations of ions that we're potentially going to be seeing, and also electrolyzer power levels. And we'll be working with the University of Exeter to do that for their kind of simulation and modeling ability, and also you know, kind of access to facilities that they already have. Now, also, we're going to start, you know, simulating the effects of injecting hydrogen into specific nodes on the network, and actually, you know, how this is going to affect customers, producers, you know, the network operators in terms of hydrogen percentages, costs, and sensitive customer requirements. And then just really looking at, you know, more tailored solutions for sensitive customers who require hydrogen in higher concentrations. Next slide, please. Yeah, well, thanks for listening, everybody, and I'll take any questions now.
Thanks very much, Charlie. That was a great presentation. I'm going to kick off with the Q&A because we've only got a few minutes. So David Elam says, thank you for a really interesting presentation on wastewater. What assumptions did you use for modeling the rainwater gathering? For example, is it assumed that it's taken from existing drainage systems? And if so, are there any impacts on the wider water system that should be considered?
Yeah, so really that's a bit of a case by case basis, really. So some of the customers that we're working for already have systems which essentially, you know, are directing the rainwater into specific channels, you know, as you say, in terms of existing drainage systems. The effects, you know, the potential effects on the wider water system is definitely something that we want to look at, you know, because obviously if they're normally discharging a certain amount of water into the system, we don't want to disrupt that. So we look to work with you know, the kind of the water operators in the area as well, to see how that would affect it. And really, with regards to the, you know, potentially using processed wastewater in the future, a lot of people have kind of licenses to discharge a certain amount at a time. So what we can do is actually use the excess that they might have over and above their discharge rate going forward. So it's a bit of a case by case answer, I'm afraid, but you know, it's certainly the effects on the wider water system is something that's really important for us to focus on.
Thanks, Charlie. Someone would like to know, is it possible that you could share a report on some of the data that you've gathered within standard engineering units? That would be really helpful to understand some of the outputs of the project.
Yeah, no, that's no problem. Just drop me an email and I can send over some stuff.
Fab. Tom Notman would like to know, how does the quality of the wastewater affect the hydrogen production and working life of the electrolyzer?
Yeah, so this is you know, going to be really a key focus for Alpha. So one of the things we want to know is how is it going to affect the efficiency of the electrolyzer, and this is going to really depend on what the wastewater is. So if there's certain ions in the wastewater, this is going to have more of effect than others. So if we just take chlorine, for example, from using kind of a more brackish type water, there's a lot of considerations we've got to take there, because if you use the electrolysis at the wrong power level, you can create chlorine gas, which obviously we don't want to do. And obviously, with every kind of byproduct that's created, the efficiency could be affected. So that's really what we're going to look at simulating in the next phase. And then also with regards to the lifespan of the electrolyzer, what we're going to do is look at different potential electrode materials that aren't so rare and expensive, so that they could be, it wouldn't be as much of an issue if they got degraded more quickly.